Hi, welcome to another session of the Potter's Roundtable from Washington Street Studio in historic Bolivar, West Virginia. I'm Phil Bernberg. Today we're going to be continuing our discussion of pottery myths, errors, and misconceptions. I'd like to continue with the subject of myths, errors, and misconceptions and talk a little bit about firing procedures. Well, one of the things that I hear sort of fairly commonly or at least implied, is that with an electric kiln and with an electronic controller, you don't need cones. Well, you do need cones, because if you really want to get good firings, an electronic controller is a great way to control the heating rate and to get reproducible heating. But you really, anytime you're firing pottery, especially for glazes, you really should be firing it by looking at the cones, because the electronic controller is only measuring temperature. And even with a program, it's not giving you the best figure as far as heat work. Glazes really respond to heat work. So you really should be monitoring the firing, looking at cones. Use the controller to get up to the temperature and the conditions you want, but then you really should be determining the end point of the firing by looking at cones. And after a while, you work out what, for your particular firing conditions or glazes, what is the necessary cone that you need to fall. Maybe it's a number 6 or a 6 cone, and when the number 6 cone goes down, your glazes have matured properly. That's the way you should be controlling the firing, not just using the controller. As far as loading the kiln for an electric kiln, I've heard comments to the effect of don't put shelves directly opposite the elements. And I'm not sure why, whether there was a concern over cracking or the fact that the shelves got too hot, but frankly, I've never seen a problem with that. And when I'm loading an electric kiln, I'm trying to place the shelves, at least some of the shelves, in a position where I can put cones on them so that I can see them through the peepholes. I'm also trying to space them far enough away from any thermocouples that I'm getting a good reading from the thermocouple. So if I had to also avoid placing the shelves opposite an element, I'm not sure how I'd be able to place the shelves at all. There'd be too many restrictions. So frankly, I've never seen a problem with putting shelves directly opposite an element. Is it possible that they shorten the life of the shelves? I guess it's possible, because the edge of the shelf would get hot quickly. But to me, I haven't seen a problem with that. So that's about the only way I can comment on that, is that I haven't seen it creating a problem. So I don't think it's necessary to do it, basically. Electric kilns, you hear the comment that, well, and this is kind of a technicality, but that in electric kilns especially, heat rises. Well, heat doesn't rise. Okay, heat can move in any direction. It's the hot air that rises. So hot air does rise, but heat doesn't rise. Heat will flow basically in any direction. And along with that, I've also heard the comment that about cold flowing into certain parts of the kiln. Cold doesn't flow either. Cold is an absence of heat, and heat does flow. Heat moves, but it doesn't particularly move up or down in any direction. But hot, yes, hot air and hot gases do tend to rise. Another strange comment that I heard a while back was that this was in relation to an electric kiln, that closed forms get hotter during the firing. And I guess that was based on the idea that maybe the thinking that if the form was closed like a teapot or a casserole with a lid, that somehow it would trap the heat. That's not true either, basically. A matter of fact, the closed form might get hotter actually a little slower. It might heat up actually a little more slowly than other pots, but it doesn't get hotter just because of the shape. And speaking of hotter, another comment I heard one time was that, actually I've heard it several times, was that shelves are the hottest components in the kiln. Of all the things in the kiln, the shelves get the hottest. And I think maybe the source of that might be the fact that when you unload the kiln, there's a chance that of all the things that are left in the kiln, the shelves might still be the hottest. Well, that's not because they were the hottest originally. It's because they're the slowest to cool down. Because the shelves are quite a massive chunk of ceramic. So once they get hot, they're going to take a long time to cool down. And the reverse is true when they're heating up. Probably the slowest things in the kiln to heat up are the shelves, because they represent a big mass of ceramic material that takes a lot of heat to get hot. So I suspect that idea may have come from the fact that if they're hot when the kiln when you're unloading the kiln, then they must have been hotter to begin with. And it's just that they take longer to cool down. Related to talking about control, and I mentioned this already, that that you don't need, with a controller you don't need cones, and the idea is that temperature is really not the best way to control firings. It's a good way to observe the heating rate and the rate of temperature climb of the kiln, but you really need to be watching heat work, because time is important when you're firing a kiln, not just the temperature. Related to gas kilns, there's a fairly common thought out there that we have a gas kiln, that propane gas burns hotter than natural gas. And again, there's a logical origin for this belief. It's not true, basically. Yes, propane burns slightly hotter than natural gas. The flame temperature is slightly hotter, but it's really not significant. But the difference is, for the same quantity of gas, let's say a cubic foot of gas, propane produces a lot more heat. So you use a fewer number of cubic feet of propane gas than you would of natural gas to provide the same amount of heating. So that might have led to the idea that, well, it must burn hotter. And it's not that it burns hotter, it's just that it's sort of, in a sense, it's a more concentrated fuel. Okay, related to heating also, there's a fairly common belief that you can't heat up bisque pots too quickly, let's say during the glaze firing, because the quartz inversion will cause cracking. Remember, we've talked about this before. There are different forms of silica, and it can exist as the mineral quartz, which is the most common form. And the quartz actually has two forms. It has a low temperature, what's called a low temperature form, and it has a high temperature form. And with a typical lack of imagination, this is called alpha and this is called beta. And it changed. If you take normal quartz that you find, for instance, out in your backyard, and it's very common, and you heated it up at around 1063 degrees Fahrenheit, it changes from the low temperature form to the high temperature form. If you had a chunk of quartz and you heated it up, there's nothing visually that you'd see, but internally, in terms of the atomic arrangement, it would change. And when it does that, it expands slightly. So the thought behind this belief is the fact that since all clay basically contains some quartz, some more than others, if I heat up too quickly when I get to around 1063, all the quartz in there is going to expand a little bit and crack the pot. Well, basically, I've never seen this to be a problem. Because when you think about it, now I'm talking about bisqueware, when you think about it, bisqueware is porous. There are a lot of holes in it. So if this is a slice of a wall, and I've got all these holes in the bisqueware, and I've got a little quartz grain here that wants to expand, there's plenty of room. This is not densely packed. It's sort of loose. It's densely packed. The little quartz grain can just kind of go crunch and expand. It's not going to destroy the whole pot. So I've never seen this to be a problem. Now, again, where this might, I'm sort of wondering, where did this belief come from? What might be, if you were refiring pots in the same firing that had already been glaze fired and you heated them up too quickly, then it's possible that both the quartz and now there might be some cristobalite in the pot. So I might have quartz and cristobalite. And when the cristobalite grain goes from low to high and the quartz goes from low to high, they both expand. Yes, it's possible that they could cause cracking of the pot, but I don't believe, frankly, that this is a serious issue with bisqueware, because the bisqueware is so porous, it isn't tightly packed. There's room for all those little quartz grains to expand without destroying the whole pot. So I'm guessing that maybe that's where this belief came from, the fact that in the same firing, people might be refiring pots. And yes, in that case, it's very possible that they could crack. Okay, another item related to firing, especially this is reduction firing, so gas or wood, especially gas, is that when you're putting the kiln under reduction and you want to keep it in reduction, that when you're making soot, that's a good thing. That's a good sign of reduction. Well, it's a good sign of over-reduction. Because as we've talked about before, what you really want to do, and you can't see it, is you really want to make carbon monoxide. That's what you make when you don't provide quite enough air to burn the fuel completely. And it's the carbon monoxide that's doing the reduction. If I go into even heavier reduction, what happens is I basically remove first I go from CO2 to carbon monoxide, and then I go to carbon. So I basically strip the oxygen and I end up with carbon. Well, soot Soot doesn't do any reduction. Soot just accumulates on everything. You see the black soot coming out, maybe the cracks in the kiln. The only reason that you'd want to intentionally make soot is if you're trying to do carbon trapping. So early in the firing, you might put the kiln into very heavy reduction and purposely try to make this very fine form of carbon, this soot, that penetrates everywhere and actually penetrates into the glaze and remains there and is trapped in the glaze. That's the source of the carbon trapping. But unless you're carbon trapping, you don't want to make soot. So if you're making a lot of soot early in the firing, unless you're doing carbon trapping, you've over-reduced. You're trying to create too much reduction, and it's not really doing any reduction at all. But you are wasting a lot of fuel. So you want to back off on the reduction a little bit. Also related to, especially I've heard this to gas kilns, and thinking about the analogy of, how a lot of electric kilns, if they don't have a downdraft fan in them, then the top of the kiln tends to be a little hotter because hot air rises. We talked about, it's the hot air that rises, not the heat. But so the top tends to be hotter. So transferring that over to a gas kiln, people will say, well, in a gas kiln, the top is always the hottest part. Well, that isn't necessarily true because it really depends on the flame path. And as a matter of fact, if you sort of do a little diagram of a gas kiln, and let's say you have, these are the bag walls. So I've got a burner that's blowing in here and a burner blowing in here, and this is my shelf stack. It's actually fairly common in a gas kiln to have the region just above the top of the bag wall be the hottest, because the flame is coming up and it's going to make its shortest path to the exit. So if on the other end of this kiln, if there's an exit, a hole leading to the chimney, it's going to come up and go over the bag wall and go as fast as it can toward the exit, which means that the flame is sort of flowing like that. So it's very common in a lot of gas kilns for not the top to be the hottest or the bottom to be the hottest, but the hottest to be right over the top of the bag wall. So you can't assume that the top is always going to be the hottest. It really depends on the flame path, which is partly controlled by the bag wall, if there is one, this separating wall, or the spacing of the shelves and the spacing of the pots. To a great extent, you've controlled or set the flame path by how you've loaded the kiln. And that's going to determine where most of the flame goes, and therefore where the highest temperatures are. Okay, again, a subject related to gas is, and this is specifically propane, is that one of the thoughts is that the propane tanks, as you're going along in the firing, freeze up and cause the gas to cause low gas pressure. And so what they typically mean is that you've got a propane tank, and you may see like a line along the bottom, and moisture condenses, but you actually may get frost. You actually may get frost condensing on the bottom, the outside of the tank. Well, what's actually happening is that we know that propane in the tank is actually in liquid form. It's not in a gas. There's liquid propane in here. And when I open and there's high pressure when the tank is sealed, there's high pressure above the liquid in the tank. And when I open the tank, and I let the pressure go down a little bit, what happens is the liquid propane boils and produces more gaseous propane. So as the level, and we know also that when something evaporates, it has a cooling effect, right? So that what happens is as the propane is evaporating, the liquid that's left behind is getting cooler and cooler because it's being cooled by the evaporation. Well, when the level in the tank gets low enough, and the remaining liquid propane has gotten really cold, it gets cold enough to actually condense the moisture in the air on the outside of the tank. And if it really gets cold enough, which it can if it gets low enough, it can actually freeze the water that's condensed on the outside of the tank. So it's sort of the reverse. It's the fact that the level in the propane tank has gotten very low, and that's causing the propane to get so cold that it freezes. It's not the freezing that's causing the problem. And so when the level gets really low and it gets really cold, the propane is not evaporating or boiling as vigorously. It's not producing as much gas, and therefore the pressure drops. So, but it's kind of a misnomer. The tank isn't freezing up. It's just the condensed moisture on the outside because the remaining propane has gotten really, really cold. By the way, normal propane boils at 40 degrees below zero. So this means that unless you're living in Alaska or Antarctica, that when you put a propane tank outside, you're going to get propane gas out of it. Now, if I put a propane, if it was, let's say, 50 degrees below zero, and I put a propane tank outside and opened the top, nothing would happen. No gas would come out, basically, because the propane wouldn't boil, because it's going to stay below the boiling point. A little bit would come out, but not much, because I'm below the boiling point. So the reason why it makes a lot of gas is because anything above 40 degrees below zero is hot enough to create a lot of boiling. Okay, wood kilns. Well, it's a fairly common belief is that you need to do a long preheat or a long candling for a wood kiln. And basically, I don't believe that's true. Now, it may be necessary because of the design of the kiln. Wood kilns typically are made with hard bricks, and it's not unusual for wood kilns to be fairly large. So it may be the fact that there's no other way you can heat it up, that because the kiln is large and it has a lot of pots and the bricks, you've got a lot of bricks, it's going to take a long time to get it hot. But I don't believe that it's necessary to take a long time to get it hot. Now, especially if you're firing already bisqued pots, we know that you can heat up bisque pots fairly rapidly. So I think in a lot of cases, it's the limitation of the kiln that's forcing you to heat up the kiln slowly. Now, if you're doing single firing or once firing, then yes, you do have to heat up slowly, at least especially early in the firing, because you have to repeat essentially a bisque firing. If you heat up the green pots too quickly, you can blow them up. So in that case, yeah, there is a real requirement to heat up slowly. But I don't think in most cases where you're wood firing already bisqued pots, I know I've done some pretty rapid firings in wood kilns and we never had a problem in terms of destroying the pots. So I think a lot of the cases it's the kiln that's limiting the heat up rate. Another comment related to wood firing is I've actually seen reports that if you burn green wood, that is wood that's not completely dry, that it actually burns hotter or that it produces more heat. And one of the thoughts about this is, again, this is this is where I think it comes from, is that there's water in the wood. So the first of all, it doesn't burn hotter and it doesn't produce more heat. It wastes heat, because the first thing before the wood can burn thoroughly is you have to drive all the water out of the wood. So it takes energy or heat to dry the wood out in the firebox. And I think the other comment I've heard is that the water, the H2O, that's coming out of the wood actually changes and breaks down into hydrogen and oxygen, and the hydrogen burns and gives you additional heat. That doesn't happen. We don't even come close to the temperature that it takes to break down water into hydrogen and oxygen. So it's called free hydrogen is what it's called. And we don't even come close in a wood kiln to produce the temperatures that would be required to break down water into free hydrogen. So that's a fallacy. So basically, that if you add wet wood or green wood to a kiln, it will slow down the heating because it's using up additional heat to evaporate the water, and it also is burning more slowly. Wood kilns also. When you're burning a wood, or even our gas kiln too, when you're burning it and you're in reduction and you open a spy hole, it's fairly common to see like a flame come out of the spy hole. And typically, if you're in reduction, the flame will be yellow. And one of the comments that I've read and heard a lot is that the way of describing it is that the yellow flames are looking for oxygen. That's why they're coming out and they're looking for oxygen. Well, that isn't true. It's the back pressure in the kiln. Basically, you've choked off the exit, or you're putting more gas in that can escape from the kiln. So the gas is going to want to come out anywhere it can get out. So when you pull open a plug or a spy hole, the gas will be forced out the hole. So it will be coming out, not because it's not out like looking for anything. It doesn't have this is more wishful thinking. It doesn't have a mind of its own. And it's yellow simply because you're in reduction. It hasn't burned the fuel completely. If the fuel was completely burning, the flame would be either invisible or pale blue. So it's not because it's looking for oxygen, it's being forced out, and the yellow is an indication that it is in reduction, that you're not burning the fuel completely. The last thought I heard was the fact that, again, speaking with wood kilns, which can get pretty hot, and also gas kilns, is that you have to be careful when you look in the kiln and protect your eyes because of the ultraviolet light. Well, there is no ultraviolet light coming out of a kiln. Again, we can't possibly get hot enough to generate ultraviolet light. The reason why the light is damaging is because it's very bright, and also because of the infrared, the heat coming out. So yes, ultraviolet light is damaging, the same way like ultraviolet light is produced in the sun. We're not quite that hot in our kilns, so we're not producing ultraviolet light. But yes, ultraviolet light is dangerous, but that's not the reason why looking into the kiln. It's the brightness and it's the heat that's dangerous to your eyes. So in summary, I guess for these three parts that we've talked about this topic, is I'd say is when you're reading or you're listening to people or looking at sources, don't take everything as fact. Do a fact check. Or even do a test. If you think something is, test something to see before you accept it. And the other thing is that, my last comment I wanted to make is that errors may not be obvious for a long period of time. I have this theory about pottery, and I think it's probably good for life in general, but that potters are walking along the edge of an invisible cliff. Because I've talked to people, and they say, well, I don't understand. I've been doing something a certain way for 20 years, and it's worked perfectly, and now it doesn't work, and I don't know what's changed. And my thought about that is the fact that nothing's changed. You've been getting away with it for 20 years because a lot of these situations, you're not guaranteed to get failure every time. You're sort of increasing the likelihood of failure. And so they've been getting away with it for 20 years, and all of a sudden something changed and now they didn't. So they've been walking along, they've been basically doing it wrong for 20 years or close to doing it wrong and getting away with it, and all of a sudden they're not. So that's part of it also, I think. So anyway, so that's about all we had for today for this subject. We hope we've wrapped up this section. Hope that this discussion has been useful. And again, we know this was a lot of information in a short period of time. So if you'd like to hear it again, you can listen to it on our podcast version. Just search for the Potter's Roundtable on your favorite podcast platform. If you enjoyed the presentation, please like it and subscribe to our channel and share it with your friends and other potters. This helps our videos get found on YouTube. Also, check out our website, www.hfclay.com, where all these videos are accessible.